Okay, last lesson here, just kind of putting it all together and going back to a previous problem. So recall that the spring problem, right? So if we could remember back, lesson 1, we did the slinky problem, and we had this oscillating spring that was going up and down, right? And we noticed that it was oscillating back and forth, but we also noticed that the more it did it, the smaller the oscillations got, which we referred to as dampening, right? So let's see if we can figure that out, put all this together here. So first off, we're going to go get the data, right? So that's that resource page. I will have that for you. It'll look similar to this, right, with that data on it, so we can put in our calculator, right? And it's going to say choose a function to model the vertical position of the weight over time. So once you have that data put in, right, it's going to look similar to this. Okay, trying to get this to turn on us, right? And so you'll have this data put in a calculator. You can plot these points, right? And if you remember when we originally did this, we had like a sine cosine function that oscillates back and forth, right? And so once we do that, right, it's going to say choose a function to model the vertical position over time. Well, what we know is what we've been doing, right? It's this exponential equation. So we're gonna use our calculator to go into stat, edit, and we're gonna do a regression equation. We're gonna choose exponential, right? And it's gonna give us an exponential equation to then predict these verticals, right? So using this data to do this, like you're gonna have some sort of exponential equation, right? And I've done this here, right? And if I zoom out, you can see that it is an exponential equation, right? Exponential decay, right? But it's gonna predict these top, right, maximum points, right? It's going to hit these, right? Again, it's based off dampening, right? So, and it may not be this exact equation I have here, but you're going to get close, right? And then we're able to predict, you know, where's it at after 2 minutes? Where's the vertical position? Okay, and we're going to reflect on that model. So what happens there is then we're able to put that function, right, as a vertical shift into our oscillating function. So if you remember, our oscillating function was that cosine function, but we need to create a vertical shift. Well, our vertical shift is now another equation because it's not a constant vertical shift. It's that oscillation, that dampening vertical shift, right? So we're able to put all this together and create the actual equation of the spring every single time, which is really cool, right? So let's move on to 107 here. So on a beautiful Sunday morning, alliteration meets a person to get coffee, right? And they want to model this idea of coffee, right? So we've done this one on a previous lesson. So we have, 180, it says that determines that the caramel macchiato is 180 degrees Fahrenheit. Wow, my coffee maker at home makes a perfect cup at 120. Okay, how long will it take to cool? Right, so 4 minutes pass and they check the temperature and discover it's 160 degrees. Then he looks at the thermostat in the room. Room temperature is 72. Okay, what is the answer to this question, right? So let's do this here. Let's see if we can... see if I can get my whiteboard up here, right? So we started at 180 degrees, right? We're trying to get to 120 degrees, and room temperature is 72 degrees, right? So we have this exponential decay, right? So we're in our exponential equation, right? We know we start at 180, but room temperature is 72. So if you remember back when we did this, right, our room temperature was plus, we moved a vertical shift of 72. Sorry, don't know what just happened there, right? But we had a vertical shift of 72, right? So that's going to take this down 72 because we're already up there, right? So this is actually going to be 108 degrees times b to the x plus 72, right? And so equals what? We know 4 minutes into it, the coffee is down to 160. So we're able then to go, okay, we know an x value of 4. We know a y value of 160. Okay, so once we do this, right, subtract 72. So we have 108 times b to the 4th. Okay, over here we would have 98, I believe. Okay. Sorry, 88. Okay. Then from there, right, we would divide by 108. Right, and we're going to get like 0.815, right, equals b to the 4th. We can then take a 4th root. Trying to make my calculator work here. Sorry guys, I was trying to find a way to show you guys, but I don't have that on me. So let's just make this work. So you put this in your calculator, right? You're able then to go take a 4th root of 0.815, right? You should get 0.950, right, as our rate. So that's our rate, okay? So now we can go back to the start, right? And we can say, all right, we want to get to 120. But we now know our rate, 0.95 to the x plus 72. Now we are solving for x. So again, subtract 72. So we'll go 120 minus 72, we'll get 48. We have 108 times 0.95 to the x, divide by 108. Okay, you should get 4/9, 4 over 9, right? Or, right, you could do a decimal, but 4/9 is great, right? So we now have 0.95 to the x. Well, what do? We take it to a log, right? So whether you log both sides or however you do that, if you just want to change to log base 0.95 of 4/9 equals x and solve. So put that in your calculator, right? And you should get an x value of 15.8, right? So that's 15 minutes, right? 15 minutes. Okay, let's go back. All right, let's look at this next one. Will it go viral? Okay, so we're talking about YouTube, right? And they call it WhoTube, right? So if you ever heard me say call it WhoTube, this is why I call it that, right? So we have a headquarters, and we want to qualify if it goes viral, right? So a self-proclaimed math magician posts a viral video of a dancing log, one with rhythm, haha, right? At 10 p.m. 3 devoted to the profession immediately watch the video. Enamored with such a cutting-edge clip, they share it with 3 other tree-trimming friends every 5 minutes, okay? Each of whom views and shares the video with 3 more friends every 5 minutes, and so on. They continue sharing the video that way until 10:20, at which they get distracted, right? And so over the next 5 minutes, 30 fellow math magicians discover the video. This incredible phenomenon continues at a rate of 30 views by math magicians every 4 minutes until 11:32. So we already have like different video